The reason we extended the trigonometric function is to the two purposes, that to handle triangle whose angle is greater than 90, and so that takes care of 0 to 180 degree. But the second purpose was the motion, right? The motion, the circular motion. Our generalization of angle and trigonometry will nicely model the circular motion. So end of the geometry, now beginning of this motion context is what we are about to enter. In the motion, it uses this arc length formula. What is this special thing about this arc length formula? S equals r times theta. Remember that? Right? If this theta appears inside the sine and cosine, it doesn't matter which measure of angle you use, degree, radian, doesn't matter. Sine, as long as you calculate it set to correct mode, it's going to give you the answer. But when this one is outside like this all by itself, it has to be in radian, correct? Yeah, it has to be in radian. So when you're dealing with sine and cosine in the context of this motion, your angle is always in radian, right? In this test, you might have to switch back and forth to degree and radian, and that's your responsibility to make sure that you are aware always if it is in radian or degree mode. So most of the angle here from this time on is all stated in radian. Since still you are familiar with the degree, we think of in terms of degree, but I want you to get used to writing angles down in radian even though we're thinking in degree. All right? So this unicircle section is just the beginning to get used to this radian measure and all that. That's just that. All right, so here's review. Same thing I'm drawing again, a circle and the definition and all that. So here is our circle. So radius r, x squared plus y squared equals r squared. Always write those down. This time is no longer triangle, so I'm going to go beyond 180 degree. I'm going to put it right here, something like this, right? Even don't have to be positive, so I'm going to angle like this. This is the angle now we are talking about. It's no longer triangle. It's a motion, right? So you see the sine of this angle theta? What is it? It's not sin, it's sign. It's a negative angle. It's rotating clockwise, right? All right. And then we have terminal point x comma y there. Correct? And then what is the final thing we write it down? Sine theta is y over r. Cosine theta is x over r. Same old stuff, right? Now, we're going to switch the perspective a little bit. Focus on x and y, not theta and the sine theta and cosine theta. So write down this new formula. When you usually write down coordinate, you write down x coordinate first, right? And y coordinate later. Correct? What is x coordinate here? You solve this thing for x. We just did that with the proof of law of cosine. If you isolate x, what is x here? Is r times cosine theta? Is that right? If I multiply r here. What about y? R times sine theta, right? So we're more about, not about sine theta and cosine, we're more about, I want to calculate the x and y, and how do we do that? And this is the, it's pretty much the same definition, but it's a little formula, baby formula. If you want to calculate the coordinates, this is how you do it. And this, we call it a parameterization. X and y are, x and y coordinates in the Cartesian plane. And how is this parameterized, circular way in the circular motion? And this is a parameterization. This parameterization goes all the way to the highest level of mathematics. So this is one that you want to never forget. All right? X is parameterized like this, r times cosine theta, y equals r times sine theta. Actually, not just in mathematics, in physics and engineering, anywhere you go, they all use this parameterization. X and y is parameterized like this. Or anything that is rotated around, not necessarily circular, is analyzed in this fashion. Very important, right? Okay, so that's that. All right. I wasn't recording this part, but it's about the unit circle. So example 1 is asking you to show that this point with x coordinate is root 3 over 3 and y coordinate is root 6 divided by 3 is on the unit circle, right? So showing means in mathematics you rigorously explained mathematically that this one is on the unit circle, not by sketching it roughly and on there. You precisely explain this is exactly on that unit circle. All right, it's good exercise. Makes you think about what all this equation is about. If x comma y is on the unit circle, it's going to satisfy that unit circle equation. And anything that satisfies this one is on the unit circle, right? This is the necessary and sufficient criterion. So we have x and y there. So I would write it like this. Compute the left-hand side of this equation we want to check. Left-hand side is x squared plus y squared equals 1. You're not going to set this one equal to 1. You just stop here. X squared plus y squared. That's the left-hand side of something we want to prove, right? So what is x here? X coordinate is root 3 over 3. So root 3 over 3, that's going to be squared. Plus, what is y? Root 6 over 3, that's going to be squared. And you don't write equal to 1 here. You actually pretend or write down all the computation. Right? When you prove or show, you don't skip calculations. So what is the first term here? 3 divided by 9. What about the second one? 6 divided by 9, right? So that together is 9 divided by 9. That is 1. So we looked at the x squared plus y squared and actually computed to be 1. So the final thing you have to write down to showing that you know what you're doing is that therefore x comma y satisfied the circle equation. Isn't that what we just did? Right, we looked at the left-hand side and showed that it's actually 1. We didn't just write equals 1. That would be a correct statement, but that's not a good proof, right? And you have to show me that. It doesn't matter how silly this one is, you have to show me this requires this computation to compute it to be 1. All right? If it is not 1, then you conclude it's a little bit off or whatever, is not on the circle. Let's look at the second one. The point with x coordinate given and y coordinate not is on the unit circle and it's also in quadrant 4. Find the y coordinate. So we're going to sketch this one. Here's a circle. And what kind of circle? It says unicircle, so it's x squared plus y squared equals 1. Now we know x coordinate, and it's positive, right? So I'm just going to pretend this is somewhere over here. There are 2 points, up there and down here, with x coordinate given 1. And they have 1 point in the quadrant 4, so this is the point they're talking about. So what is the x coordinate here? Root 3 over 2. Y coordinate? Not known. Okay? So that's the point we're looking for. Then you can use the circle equation to do that. So what is x? Root 3 over 2 squared y squared. This is supposed to be 1, so you solve for y. This seems like a simple one, but you have to think about it a little bit at the end, so I'm going to make an exercise. Compute y coordinate here. Well, you all got down to this y squared equals 1/4, right? So what is y then? 1/2? but it's down there in the fourth quadrant, right? So you have to choose negative. Algebraically, whenever you look at y squared equals something, you always algebraically have two possibilities, 1/4 and negative 1/4, plus minus root of, and always think about which one is the right choice using information. If not, sometimes you have to conclude both are correct answer, both are possibilities. And here, they said it's a quadrant 4, so it has to be y equals negative 1/4. That's a little exercise. Think about the points on the circle. There's no trigonometry or anything in here. So about the circle and the points on the circle. Now we're entering the trigonometry here. Now you notice that they're using t, no longer theta, right? The reason is that theta was 4 angles, and when you enter motion, that angle is the magnitude of angle is also used as a magnitude of time, constant angular speed. So they use this sine and cosine to model the motion in terms of time. So they mix this magnitude of angle and magnitude of time. So right now it says t equals 3 pi. Then you automatically think about 3 pi radian, correct. But the reason they're dropping this radian measure is to mix this one. When they write it t equals 3 pi, they might mean 3 pi seconds. Do you know how long is 3 pi seconds? 3 pi seconds is a little less than 10 seconds. Does that make sense? Pi is 3.14, so if you multiply by 3, it's 9.3 seconds. That's the number we're looking at there. T meaning, from the relative time position 0, pi seconds before. That's the notation switch we're looking at here. So here's a unit circle. Example 3 is easy. So what kind of circle? Square plus y squared equals 1. Unit circle. Now this is where theta equals 0, right? 0 radian. Now we're using the t. T equals 0. What is t? The magnitude of angle. 0 radian, right? So let's look at this one. 3 pi. How about pi? Where is pi radian? 180 pointed here. So we've got to do it two more times, right? 1. And second time you get 2 pi. Third time you get 3 pi over here, right? So this point right here has t equals 3 pi radian, right? That's location. But you can also look at it as a 3 pi seconds later, this dot is circling around and arrived at here. That's how they're going to mix this one. Angle versus that many seconds later, the location of this one on the circle. Alright, so what is the coordinate here? If it's a unit circle. Y coordinate 0, right? X coordinate? And then negative 1? Because it's radius 1 there. Correct? So after 3 pi seconds later, roughly 9.3 seconds later, that particle is on their location negative 1 comma 0. But it's really 3 pi rotation, 3 pi radian rotation, right? How about negative pi? Where is negative pi here? 180 point, exactly the same point here. So this point, you can arrive here in many different ways. That's what we're looking at here, right? Last position doesn't really tell you how you got there. The first one here, one full rotation and half more rotation, and this one is a clockwise rotation, half rotation, things like that. So how about negative pi over 2? North pole or south pole? South pole in here. That's where t equals negative pi over 2 is. And the coordinate there? X is 0, y is negative 1, right? Yeah. So those are the coordinate points. That's, you can also do that with the top point. Those were not too bad. So let's look at somewhere in the middle in here. I'm going to look at negative pi over 4 first. So you look at it as negative pi over 4 radian, right? So I'm going to draw a unit circle. right. Pi is 180 degree, right? Pi over 2, 1/2 of it, 90 degree. Now here's a pi over 4, another half. So that's going to be 45 degree, right? Or you can convert it secretly. Convert it and then realize it 45 degree. But negative 45 degrees, so that's the angle right here. That's the angle they're talking about. This is a t radian. All right, that's a part A. It's a t radian. That's what we're doing. I don't know what the terminal coordinates are, but that's what they're asking you to find. So the backward 45 degree, we know about this thing, right? So I'm going to exit that unit circle, go to our favor circle. So what is a favor circle if down there is a 45 degree? Let me first sketch it and you let me know what that is. So here is that same 45 degree here. Backward, negative, right? And when we do this special thing, we usually create this triangle, right? Right triangle, remember? So if this is 45 as a triangle degree, and what kind of triangle we're looking at? Special triangle, right? What are the sides here? 1, 1, and here, root 2. This is not unicircle, but from there, we can calculate the same sine and cosine. All right, so let's do that. What is the coordinate here? 1 comma negative 1, right? There's no square root in this coordinate. From here, we calculated sine this angle here. This is not 45, although you think about it as a 45. When you do this, sine and cosine, we have to stick to the radian now, okay? What was the angle? Negative pi over 4, right? What is it? This is the angle negative pi over 4. And how do you compute the sine part? Y coordinate, right? Which is negative 1 divided by root 2. Is that right? How about cosine? Negative pi over 4. X coordinate, which is positive 1 divided by root 2. Is that right? Good. This is not unicircle, but it tells you what sine negative pi over 4 and cosine negative pi over 4 is, right? And I said that there's something special about the unicircle. Anybody remember? What is so special about the unicircle? I'm going back, and here, this is where I introduced unicircle, right? Exactly the same thing, but what's special about the unicircle? Not only x and y coordinates are related to cosine, sine, the cosine value and sine values is exactly x and y coordinate. Okay, so that's the connection. Down here, this is a unicircle, x squared plus y squared equals 1, and we want to calculate x and y, right? What is this connection? Is cosine negative pi over 4. Is the sine negative pi over 4. Isn't that what I just showed? But what is cosine negative pi over 4? We calculated here in different circle, right? I use a different circle to calculate this guy. So this information that we use a different circle is a 1 over root 2. And this one in here, we looked at different sides of circle and figure out what these values are. And that values actually becomes the x and y coordinates on the unit circle with the same angle. Does that make sense? So since we're running out of time a little bit, we're going to do negative 5 over 6, pi over 6. We're going to do that together, part C. So think about the angle, negative 5 pi over 6, and we want to compute the coordinates. So we're going backwards, just like we did before, with pi over 4. Alright. If we start here, going clockwise, do you know where it stops? It stops at fourth quadrant or third quadrant or second quadrant? Where does it go? If it's negative 5 pi over 6. Third quadrant, right? So it's somewhere about here. So that's the... So if it's not clear, you have to convert that secretly, convert that into degree, and actually get an idea that that's the t is a negative 5 pi over 6, right? That's where we stop. And we're going to calculate this one in here, x and y. All right? So what is the remaining angle here toward to the x-axis? That's the 30 degrees, correct. Yeah. 30 degree in radian, pi over 6, right? So I'm going to pretend like this. So we're going to go to that circle, different size of circles that we understand better, and see if we can figure this one out. Here's a circle at a different size, and this is the angle 30 degree here. All right? Mackenzie, can you close the door for us, please? Yeah. Let me write it down. Here, that angle is pi over 6, right? And we're going to do this triangle. And knowing that pi over 6 is a 30 degree, right? What kind of triangle are we looking at? Special triangle. What are the numbers? 1, 2, root 3. 2 is definitely here. Is a vertical one or a horizontal one? Vertical one, right? Because it's just smaller, so that's root 3. So what are the coordinates here? No, 1 is a vertical, so 1 should go, I think, here, down, and to the left, so it's negative root 3 as well. So that's the coordinate, right? Okay. So, but this is the angle for negative 5 over 3, 4 over 6. This is not terminal point for pi over 6. We just looked at that angle to figure out the triangle. This is a terminal point for what angle? Negative 5 pi over 6, right? So when you write down sine of negative 5 pi over 6, you use y coordinate, negative 1 divided by radius. What's the radius? Just 2, right? Radius is 2. How about cosine? Negative 5 pi over 6. X coordinate, negative root 3 divided by radius, which is always positive, and here is 2, right? These are just the value. And this value becomes x and y coordinates on the unit circle. All right? So what is x here? That number you see, negative 1/2. And what about y coordinate? That number you see it in here. Sorry about that. X is supposed to be cosine value, right? So I did it wrong. X is supposed to be cosine, so it's negative root 3 over 2. Y is a sine value, negative 1/2.